This episode of Stories from the NNI is taken from my conversation with John Rogers. I couldn't help asking him about a picture from his lab website, and he talked about what it took to figure out how much power can be harvested from a heart. I noticed on your website the one image, one of your devices on a heart, and you refer to energy harvesting. And that's an area of particular interest to me. I think that as we move to the Internet of Things and embedded sensors and having the ability to harvest energy from the surroundings is going to become more and more important. Can you talk a little bit about the nanotechnology that's involved in that application?
Yeah, sure. I think power supply is always kind of an important and an interesting and challenging topic when it comes to these kinds of body integrated devices. Batteries are getting better over time, but still battery life correlates very strongly with the size of the battery, and the dimensions are not decreasing at any kind of trend comparable to the size reduction that we've seen in transistors, for example, over the years. And so I think moving beyond batteries becomes important, especially for these kind of very thin, flexible, conformal devices that we've been talking about. Where do you put the battery? And the answer is maybe you don't use a battery because it's a big challenge to figure out how to do that integration. A bulky, massive, rigid battery, where do you put it and how does it fit in the context of these thin, soft devices? And so really for that reason, we and others as well spend a lot of time thinking about alternative sources of power that eliminate the need for batteries. Mechanical energy harvesting is certainly one opportunity. Living systems are characterized by motion. Motion involves kinetic energy at some level, and if you can convert that energy into electrical power, then maybe that's a way to enable operation of these kinds of electronic platforms. So the device that you mentioned was designed to integrate with the surface of the heart, which is a natural point to consider for doing this kind of mechanical to electrical energy conversion, because the heart's always moving. Those particular platforms, they exploited some of the highest performance piezoelectric materials, so materials that allow this kind of mechanical to electrical energy conversion. But instead of the usual thick rigid formats, we created ultra thin sort of ribbons that have nanoscale dimensions, and by virtue of that small thickness also offer very low bending stiffness, so they become mechanically flexible, which is a key attribute. If you want to mount on the surface of the heart without constraining its natural motion, it needs to be able to bend without any significant mechanical load on the heart. And so these sort of nanoscale ribbons of these piezoelectric materials, lead, zirconate, titanate in particular, was a good materials choice for that particular applications. So we created arrays of these kinds of ribbons and then just demonstrated in practical sense how much electrical power can be generated in that way. And maybe equally interesting part of the overall research effort is what determines the limited amount of power you can get from the heart. If you think about just the mechanical motions of the heart, there are estimates that would suggest that the corresponding power is in the range of 1 watt. And you would think with all that mechanical power, if you could convert even a small fraction of it into electrical, then that would be easily sufficient to satisfy the requirements of integrated circuits and sensors and radio systems and all kinds of other electronic hardware that you might want to consider as an implant, pacemaker, or any other kind of device where the power budgets are typically, even including radio operation, maybe in the range of 10 milliwatts, a small fraction of a watt, right? The power associated with mechanical motion of the heart. What we found is that you can't even get to that level of harvesting, because the heart, if it experiences a mechanical load on its surface of any significance, it will transition into an irregular heartbeat, an arrhythmia that's difficult or impossible to recover from. And I think that level of sensitivity hadn't been examined in the past, but it turned out to be a very important part of the research, because we could engineer these flexible devices by controlling their nanoscale dimensions to achieve any kind of bending stiffness, and then we could just look at what level the bending stiffness needed to be in to avoid this kind of adverse consequence. And from that, we were able to determine that you could reliably capture microwatts of power, but not milliwatts. And so it demonstrated that you can do harvesting, but maybe not as much as you expected. And I think the consequence is that stronger motivation for developing ultra low power electronics. So that was the nature of that project. It involved a very strong biology and physiology component, but in the context of these sort of nanomaterial platforms for doing this kind of energy conversion.
This particular application required interdisciplinary interactions. It seems like you may need an MD on your team.
Yeah, absolutely. I mean, I think if you're going to do work of this flavor, it really needs to embed that kind of clinical perspective. I mean, at the end of the day is to have some kind of broader impact, right? And if you don't have that clinical base of knowledge embedded directly into the research, then there's a risk that you end up working on problems that aren't really impactful, right? So in that particular study, we had as a co-author prominent interventional cardiologist, Marv Slepian from University of Arizona's Sarver Heart Center and medical schools. So he was actually an integral member of the team. And so the interaction essentially involved our development of these kind of flexible energy harvesters in the laboratory, in the academic lab, and full characterization of those devices from a lab bench experimental standpoint, coupled with theoretical modeling as well, so that we can establish, a detailed understanding of all of the physics and the materials aspects of these technologies. But then Marv's involvement was at the level of the animal testing. So we would build the devices. This is when I was back in Urbana. I've since moved to Northwestern. But when we were doing that work, we were in Urbana. So we would do all of the physical science research and the engineering development in Urbana. And then I would send students out to Arizona and they'd work with Marv on animal studies. And these studies were quite elaborate, so they involved multiple different animal models. It was sort of an iterative back and forth between Marv's team and my team. Coupled into that, I mentioned, was a theory team as well, developing the analytical framework and the models for understanding the operation of these devices. So I would say more generally, not just collaborations with clinicians, but I think these days, if you want to make research at the system level, the overall goal and aspiration of your programs, it intrinsically becomes highly multidisciplinary. And so I think one thing that we've done well over the years is that we've been able to find good collaborators and work productively with them. Not only on the clinical side, but on the theoretical side, the electrical engineering aspects sometimes will involve collaborators as well. So many of our papers involve large teams, multidisciplinary collaborative teams, and I think that's a good way to make progress in modern scientific research, because a lot of the grand challenges and the problems you're trying to tackle are intrinsically multidisciplinary, and so it really demands that kind of approach.
Thank you. That was a great summary, and I think that some say that the National Nanotechnology Initiative has actually been one of the places that has really brought that interdisciplinary approach to advancing science, because it existed at the intersection of traditional boundaries, especially 20 years ago when we were just getting things ramped up. I hope you enjoyed this excerpt from our conversation, and I want to thank John again for taking the time to talk with me. And thank you for listening to Stories from the NNI. If you would like to learn more about nanotechnology, please visit www.nano.gov and check back here for more stories.